In this lesson, we compare three cache replacement policies on a thrashing workload: least recently used, static re-reference interval prediction, and random. Our workload is adversarial. The working set equals the cache capacity plus one item. We will predict which policy wins and why, both mathematically and graphically. To build intuition, we will use a concrete example with capacity 4 and 5 items labeled A through E, accessed in a repeating round-robin sequence B, C, D, E, then back to A, and so on. This pattern is the classic worst case for least recently used, one more distinct block than the cache can hold. First, least recently used. Intuitively, least recently used keeps the C, most recent distinct items. But with C plus one distinct items accessed in a cycle, the next item you want is always the least recently used one. That means least recently used will miss on every single reference in steady state. Let's see it on the 4-slot cache. Mathematically, for capacity C and working set C plus 1 in this pure cycle, the miss rate is 100%. Now, static re-reference interval prediction, often pronounced SRRIP. It assigns each line a tiny counter called our PV for re-reference prediction value. On a miss, new lines are inserted with a long prediction, for example value 2, when the maximum is 3. On a hit, the counter is set to 0, meaning the line will likely be used soon again. Victims are chosen among lines whose predictor is at the maximum 3. On our thrashing cycle, SRRIP converges to a very stable pattern. Exactly one specific item always misses, while the other C items stay resident and produce hits on every reuse. Let's visualize a steady state snapshot for capacity 4. Mathematically, that means one miss per 5 references, so the miss rate is 1 over C plus 1. Finally, random replacement. After each miss, the cache evicts a uniformly random resident line. On our cycle, random sometimes keeps the next few items, giving hits, but it also randomly throws away things you will need soon. We can approximate the steady state hit probability using a survival argument. Between two uses of the same item, there are about C other unique references. If each intervening miss has a 1 over C chance to evict our item, then the survival probability is roughly 1 minus 1 over C, raised to the C power, which is close to 1 over E. So the miss rate is about 1 minus that, around 36 to 38%, which is clearly worse than 1 over C plus 1. For capacity 4, that gives a miss rate near 0.316. Let's summarize with a bar chart of miss rates for capacity 4 and 5 item cycle. Least recently used misses on every reference. SRRIP misses once per 5 references, which is 20%. Random misses roughly 32% by our approximation. So the winner on this thrashing workload is SRRIP, then random, then least recently used. Why? SRRIP protects reused lines by inserting new lines as long distance and only promotes on real hits, avoiding self-destruction on the cycle. Least recently used, by contrast, always evicts exactly the item you will need next on this pattern. Random sits in between. To wrap up the math, for capacity C with a working set C plus 1 in a pure cycle, least recently used has miss rate equal to 1 because each reference is to the least recently used block. Static re-reference interval prediction converges to 1 miss per cycle, so the miss rate is 1 over C plus 1. Random is approximately 1 minus 1 over C to the C, which is around 36 to 38% for moderate C. Therefore, SRRIP wins decisively on this adversarial thrashing pattern. Intuitively, least recently used chases its own tail on this cycle, always evicting exactly the item you will need next. Random sometimes gets lucky, but also discards items you will need soon. SRRIP plays defense. It treats new arrivals as long re-reference, keeps recently reused lines safe, and so it avoids the cascade of self-evictions. That is why it wins on thrashing.